Okay, so we're going to talk about munging healthcare data with Python. You get a giant mess delivered to you. How can you extract useful information? Well, major steps in prepping data from your data pipeline, so things you've already brought in. First, munging. So you want to extract information from unstructured or semi-structured data, and you want to pre-process it into rectangular data. That is how most of your relevant AI and machine learning algorithms will work, with rectangular data. You also want to clean your data. You want to match records, so to the extent you are able to take data from separate sources that might contain the same individuals, you want to be able to recognize those individuals so you can get the maximum information from your data. You also want to anonymize data, and personally I think this is a matter of ethics. Even where people have freely provided data to you that is not sort of legally protected, you still want to make sure that you're not giving away people's personal details, because there is some expectation of privacy even when it's not regulated. So let's talk first about extracting information from unstructured or semi-structured data sources. There's lots of easy things you can do, and that's what we're going to focus on. So you get free-form text typed, hopefully. If it's handwritten, you have OCR that you need to work on, and that's beyond the scope of this presentation. But let's say you have typed notes either from a doctor or from a user of your app. First, you can do easy things like search for the presence of words, because there are certain words that are just really revealing, or roots of words. So for example, you might just search for glyc, that root, to find blood sugar concerns, and that's going to limit you to only a certain sort of subset of people, right? If someone has had their blood glucose tested or has a glycemic indicator of some kind in their records, you know that person has something going on with their blood sugar. You know that means they didn't break their leg or they're not a cancer patient. There's something more specific. You can also use regular expressions to extract quantities or dates of interest. So sometimes you'll get records, and that's what we're going to look at right now, where the data isn't entirely unstructured. They maybe come in rows where it says, date of surgery X, date of surgery X, and you can sort of extract those and make them into easier to access data. Anything fancier is going to require some natural language processing and probably a hand-marked training data set. So that's something that's going to be fairly expensive, probably worth doing, but we're not going to talk about that today. So we're going to look at extracting information from semi-structured data, and we're going to do a code example. In the Git repo, in the overview section, this is going to be in the data munging folder, and I would call your attention to a .txt, which I actually downloaded from the VA healthcare system, where they show a sample of one way that they store their data. And then we're going to use a Python notebook called Extracting Data from Medical Records. And we're going to do two things. We're going to think about generating medication reminders, and we're going to think about extracting a vaccination history from the record. So this is the .txt file that I downloaded from the VA healthcare system. What you can see is they call it the My Healthy Vet Personal Information Report. This is one way they might provide information to someone who wanted to see their medical records. And when I look at this, to my mind meets the definition of semi-structured data, in the sense that it's not free-form text. If we scroll down, we can sort of see that there are fields filled in. It's more like a form. So if I look at this, I see that I can actually hope to extract information without being a natural language processing expert. For example, I can extract a table of treating facilities for this person and get an idea of where they live geographically, how many times they've moved, things like that. I can easily extract their address. I can get their contact information. So all sorts of things that I might want to do in an automated fashion. Say if this person gave me this medical record and said, put all of this in a mobile app and make it really easily accessible for me, that's something we would be able to do, because this is regular text. So when I look at this, I think, okay, I can do a regex. And one thing that I noticed that was interesting here is that we can look at the vaccination history. So let's go back and look for immunizations. That's an entire section, VA immunizations. And just like with earlier text in the file, we can see that the immunization history comes in a very regular format. So even though it is natural language, it's formatted natural language. So I can actually hope to extract information about these immunizations and put it into a rectangular data set. So to do that, I'm actually going to use a regular expression search string. You can see my regular expression search string here. If you are not familiar with regex, this is something that can take a while to master, but the beauty of regex is it helps you do things like this, like recognize an immunization and a date received. And actually what we are going to do is try to extract the immunizations from this portion where we have immunization : and then we have the name, and then we have a new line, and we have date received, and we have the date that the immunization was received. And we can see there are two sections, and we're going to try to extract from both of them. So one of them is immunizations provided at the VA, and another one is self-reported immunizations. So we're going to try to get both of those into our data set. So with our search string, we are looking for immunization plus white space, and we have a capture group trying to get whatever comes after that white space and before date received. And then after date received, we also try to capture the text that comes after that. So the idea is we'll get both the name of the vaccination and the date of the vaccination. So if we run this and take a look at our results, we can see we've got 1, 2, 3, 4, 5, 6, 7 vaccinations. And I'm going to just go and check that against the records to make sure I've captured everything. And I see that indeed that does capture everything. And I also notice some interesting things, like those administered by the VA are in caps. Those not administered by the VA are not in caps. And I can see the same thing here. I also see that the date format is different depending on whether it was administered at the VA or not. First thing I'll do is stick that in a pandas data frame. If you're not familiar with pandas, it's a way of storing data in a table form, much like Excel or a SQL database. And it makes data very easy to examine and manipulate. So here we can see what our data frame looks like. I named my columns vaccine and vaxdate, and I have them here. Now this is not entirely interesting yet to me because I have this non-standard date format. I want to be able to treat these things like actual dates. So what I'm going to do is I'm going to strip out the at in this information, and I'm also going to think, I don't really care what time the vaccine was administered. For certain things I might care about time of day. For vaccination, I only want to know approximately when they were vaccinated. So I'm just going to cut this out. I've got a strip extra definitional function here, and the idea is it will just grab the date and it will drop this junk that I don't need right now. And that's because my purpose right now is not interested in time of day. And I'm going to put that in as a real date. I'm also going to put it into a pandas timestamp format, which means it's actually treated like a time rather than just a string. And if we now look at our data frame, we can see we have actual dates. And I will also use the metadata available, right? So the fact that this at is in the date format actually tells me indirectly which one of these are clinically documented because they were administered at the VA. Those I might trust a little bit more, so I want to have a flag that they were clinically documented versus something the patient just thinks they remember. So if I mark that, I also have trues and false for my clinically documented. That will be very helpful to my data scientists. If they start doubting some of the self-reported, they can easily filter down just to those that are clinically validated. I also want to put these in order, right? Right now I've got things 2012, 2011, 2013, 2010. So I'm going to just sort my values, and if I look again, now I've got my vaccinations. They are in order of when they were vaccinated. I am going to also put everything in caps so that I can match them against each other. You see here I'm going to match vaccinations. So tetanus versus tetanus, uppercase versus lowercase, are not going to automatically match. I cut down to the beginning of the name of the vaccination and put everything in caps so I can easily match them. I'm going to set that as my index. And the beauty of this is I can also figure out how long it has been between vaccinations, right? So for example, I am grouping by tetanus. I have a tetanus in 2010 in July. I have a tetanus in 2012 in December, and I have a tetanus in 2013. And so what I can see here is I can see the time between vaccinations. So from the first vaccination to the second one for tetanus, I had 873 days. And for the second vaccination to the third, I had only 31 days. So I've already seen something really interesting here that was not spelled out in the semi-structured data, but that is available. And that is that the first vaccination was probably just a routine thing or didn't need a follow-up, whereas the second incident with the tetanus vaccination most definitely was in response to some problem. And I know that because nobody just gets 2 tetanus vaccinations within 31 days. So here you've seen a case of where we have gone from this kind of text, which takes a long time to read and is not machine readable in the sense of being accessible to algorithms, to something where I not only have now the information sorted and tagged according to whether it's clinically documented, but I can easily figure out the exact history per vaccination, which is something that if a clinician had to read it, they're highly paid, minimally available professionals who don't have time to be counting days between vaccinations, but this computer program can do it really quickly. I can also do medication reminders in the same way, so I can use a regular expression to extract information about medication. If I do that, I can see all the medications the patient is on. I can put this in a data frame as well, and if we take a look, here are some of the bits of information I've extracted. Medication name, the directions, the status, so some of them are active and expired, refills remaining, when they were last filled, when they were initially ordered, the quantities and the day's supply. And what's good there is I can look for the ones that are active and try to generate reminders. So if I have a mobile application of some kind, I can actually send messages to my patient or my user saying, hey, I notice these medications are active and you might want to take it because you're supposed to take it every day. So for example, I can find how often based on the word every, which is only one way a clinician would document it, but the way that I notice they're using here. I can then figure out how often they need to take them. I can get the directions and how that actually translates to a time unit, and I want to just check that. So take by mouth every day, the time delta is day. Take by mouth every day, again, the time delta is day. I can then generate a time range and say, okay, well, give me 30 days. Give me a list of dates for 30 days into the future. Or let's say it were every 12 hours. I could generate a date range from now with every 12 hours, and maybe I only want 10 of them, and I can easily do that. So here I want to just give you an idea of things that can be done very easily with Python to take data out of this semi-structured format we saw and turn it into real AI that can change people's lives. Okay, so the other thing you're going to want to do once you've extracted data from unstructured sources is you're going to want to pre-process it. And it's funny because this is the bit that is easier, but it actually comes after, right? So the more difficult part is extracting data from unstructured or semi-structured text. Once you have that data, or data that is already naturally rectangular but not processed, you want to pre-process and do a few things. These are just easy to make mistakes that will make your life difficult. So you never want to get to the point where you have modeled a problem, possibly spent days or weeks thinking about what makes people sick or what makes certain patients really expensive or what makes certain hospitals not as safe as others, and then realize that some of your conclusions were based on not getting all of the data that you could use or were based on misreading that data. So a few things you always want to do. You want to remove alphanumeric case dependencies, so get rid of special characters. Those special characters are often subject to typos. And you want to do things also like convert to all upper or lower case. And the idea here is, for example, there's many ways to spell Mary Ann as a name, right? You could have it as 2 words, you could have it hyphenated, you could have all sorts of other variations, and especially because the person is often not writing their own name, but having someone else transcribe their name. So you want to get rid of all those likely sources for typos and irregularities. You also want to convert timestamps to local time. So often in databases or when an app sends you something, you're going to get data in UTC. People don't work in UTC though, right? People work according to their local time zone. So when you are doing analyses where time of day or day of the week or day of the year matters, remember that that is affected by time zone. So something that's marked at, as 10 p.m. in UTC is actually 5 p.m. somewhere else, which is a much more reasonable time for certain events. So in our example of a vaccination history, I didn't actually care about time of day, but if I were looking at blood sugar or surgery mortality, I certainly would care about time of day and would make sure to localize times. You also want to do unit conversions. There are certain health metrics that can come in more than one kind of unit. Sometimes that's geographically determined. For example, in the US, diabetics almost all use milligrams per deciliter, but some countries actually use both. So for example, certain European countries use both milligrams per deciliter and millimoles per liter, and people just have a personal preference. So when you get data, you want to confirm they're all in the same units. And of course, it always depends on your data. So you always want to just sort of take a free-form look at your data, see if there are obvious problems, right? You are still the best form of AI. The data scientist or the data engineer is the best form of AI at the start. So you always want to think, are these natural? Are these the numbers I expect? You also want to think about how you got the data. So if you are using a mobile app, you might want to look at the interface the user use to input the data and think, well, what kind of mistakes could they make, or what might they misunderstand? And that can be another way to think about how your particular data needs to be pre-processed. So we're going to look at a code example here with Python, thinking about how we can clean our data. So in this case, I'm just manufacturing some synthetic data to point out some of the issues you might run into. If you look, I am making a data frame, and I will show it to you, where we have got information about how much somebody walked, what units they walked in, what their first name is, what their last name is, what their usual location is, and also some med timestamp that is just telling me they took their medication at X time. And you'll notice this is in seconds since the epoch, right? So if you are a programmer, you know we count from Jan 1st, 1970, UTC. But this is not in very useful information when I want to have some intuition about people's actual experiences. So you see a lot of the common issues you're going to run into here in a data pipeline. One is if we look at the first name, like I was talking about, we've got say Latoya with an apostrophe, we've got an Anne Marie with a space, we've got a Billie Jean with a hyphen. Depending on who wrote those down, that may or may not be the way that person actually spells their name, and it may or may not match all of their medical records or legal records or what have you. And similarly, we can run into that with last names, right? So a hyphen in a last name or an apostrophe in a last name. So what we're going to want to do is just remove those alphanumeric case dependencies. We're also just going to convert everything to uppercase so we don't run into cases of some people capitalize a certain letter but not others. And this is all very easy to do in Python. So first we'll just convert everything to uppercase, and if we take a look at our data frame, we can now see everything's uppercase, so that's one way that things will match more between records. And then we are also going to only include things in names that are alphanumeric. Instead of making your own list, you usually just want to require alphanumeric, and you can do something like a list comprehension where you only include a number if it is alphanumeric. And Python already has an automatic function to do that for you. Whenever you can use a pre-packaged way of solving a problem, that's usually less error prone. So if we apply that, we can also see things like those hyphens and spaces have been removed. This way, Anne Marie Brown's name is always going to appear the same, regardless of how people might have misspelled it, despite her instructions. Converting timestamps to local time. So we have people from Chicago and New York. I'm going to have some kind of dictionary to map their location to a particular time zone. You have to have some way of getting at their location to get their time zone that is not always intrinsically stored with timestamps. So we will do that, and then we will define a function that will actually, depending on someone's location, convert the time zone to their location. We write this function, and then we can get an actual timestamp out of that. And if we look now, we have an actual timestamp. We see that it's human readable, right? So instead of this, hundreds of thousands of seconds type timestamp, we have something we can read. And we also see these are sensible timestamps, right? Things happened at 4:15 or 10:15 or 1:17 or 12:03. These are sensible times, and that's something you want to verify, right? Did my time zone conversion go correct, or am I saying that people in Chicago are doing things at 3 a.m.? Because if I'm saying that, I'm usually wrong. So you can see here that with some fluency in Python's way of handling timestamps, you can do a lot very quickly. Conversions, right? Maybe you don't remember this since high school physics, but it's good to be able to convert between units. That's usually just a matter of multiplying by some conversion factor. So for example, here I need to convert kilometers to miles or miles to kilometers so that they are all the same. So I am going to do that, and you always want to leave, just like an audit trail in personal health information, you always want to leave an audit trail of how you converted your data. So a few things I'm doing here. One is I have my conversion factor defined somewhere, hopefully centrally. So if I were to realize my conversion factor is wrong, I know that all of my data has at least used the same conversion factor and I can easily fix it. Or if we're just going to update it, maybe it wasn't wrong, but we want more accuracy, we can also very easily update our code just in one place. And I am also, rather than converting an existing column in my data frame, I'm making a new column so that I can inspect what I've done, and also so that I don't lose that original data. I never want to lose original data. But you can see here now I've put in my real time stamp and my miles walked, and so now I can start processing my data. And again, just as a reminder, your best bet in addition to these standard steps is you always want to look at your data. So think about how you got your data and what mistakes people are likely to make. If you got data from a walk-around community survey, people very likely misspelled names. If you got data input from a user interface, it's probably maybe typos in your keyboard. You also can sometimes look for bimodal plots of data. Most human healthcare data, apart from when you know you have distinct populations, most data will be sort of unimodal, some kind of normal distribution. So for example, if I'm looking at the distance people have walked and it's bimodal, I'm going to be more likely to think that's a miles-kilometer issue rather than that there are distinct walking populations. I could be wrong, but it is a warning sign. So those are a few good practices for pre-processing your data before you're analyzing.